Hello, my name is Eduardo Pavés, and I will be presenting our paper Spectral Folding and Two-Channel Filter Banks on Arbitrary Graphs. This is work done with Benjamin Giraud, Antonio Ortega, and Philip Chow. I will start the talk by going over some general concepts of graph signal processing and filter banks. Then I'll present our results and experiments, and I'll finalize with some conclusions on future work. So in graph signal processing, we consider graphs. Graphs are a collection of nodes and edges connecting these nodes that represent relationships between them. Edges might be weighted, and in graph signal processing, we're interested in analyzing graph signals, which are functions on the nodes. One of the main tools to analyze graph signals is the graph Fourier transform. So the first thing we need to know is we have is a variation operator M, which is a positive semi-definite matrix. Some examples include the Laplacian and the normalized Laplacian. Then the Hilbert space is introduced by a inner product matrix Q, which induces an inner product and a norm. And based on Q and M, we have the fundamental matrix C. Now the MQGFT is defined as the eigenvectors of Z. Of course, when Q is the identity matrix, we obtain a traditional GFT. This MQGFT has Q orthonormal columns. And also we can define spectral graph filters in the traditional way using this new GFT, when H is the filter kernel. Now, a two-channel filter bank consists of several spectral graph filters, H0, H1, G0, and G1. This system basically inputs a signal X and then produces a reconstructed or processed signal X hat. A refers to approximation coefficients and D to detail coefficients. The downward arrows are the downsampling operators, which are basically just on graphs correspond to selecting a subset of the entries of the signal. For example, as shown in the picture on the right. And upsampling is basically zero padding with zeros, as shown in the picture. In practice, you don't use a two-channel filter bank, you iterate several of them. And then this produces several detail coefficients denoted by DL at different resolutions and approximation coefficient A0. And then usually in applications, you take these coefficients and you do compression, denoising, or other algorithms. Now, on graphs, we're interested in filter banks that have several useful properties. One of them is critical sampling, which basically means that the size of the input is equal to the size of the transform coefficients. Another property we're interested in is perfect reconstruction, which basically means that the system is invertible. And finally, energy preservation in the norm Q, which is useful for stability of algorithms. And of course, we need the overall implementation of this to have some low complexity, so we can use these methods for high-dimensional signals on large graphs. Now, for traditional signal processing, filter banks have been studied for many years, and there are actually several good solutions that obey all these properties. And also, there are several techniques to implement them with fast algorithms. However, in graph signal processing, since it's a more new field, there are fewer solutions, and usually they're not as useful, as we will see in the next slides. One of the most sort of complete theories are filter banks on bipartite graphs. A bipartite graph is one graph that allows edges to go from one set A to one set B, and no edges are allowed within each of the sets. Examples are the line graph and the grid graph used in traditional signal processing. So in this framework, you basically use the bipartition as your sampling sets. They also consider the normalized Laplacian as the variation operator, and the GFT based on the normalized Laplacian and the identity inner product with their corresponding graph filters and fundamental matrix C. So these filter banks are basically possible because the normalized Laplacian of bipartite graphs satisfies a spectral folding property. This means that, let's say, if U is an eigenvector with eigenvalue lambda, then you can always find another eigenvector called JU with eigenvalue 2 minus lambda. How you construct J? Well, J is a diagonal matrix that has its diagonal 1 and minus 1 depending on the bipartition. So in practice, what this means is that if this is an eigenvector, then you just look at the entries on the set B, and then you flip its sign, and then therefore this is also an eigenvector. Naranja and Ortega in a 2012 paper showed that perfect reconstruction filter banks can be obtained if the kernel satisfies these two conditions. And they also show that you can have energy preserving filter banks if you have these. In addition, you satisfy these two conditions. And there are many, basically based on these papers, there are many applications on compression, on signal processing of graph signals, and also there has been a lot of work on extensions, on filter designs, on improvements of this theory, and so on. Now, even though they have this theory has a lot of good properties and it's like has very also practical implementations. The main drawback is that actually you need to have a bipartite graph, and also you need to have a normalized Laplacian. And this is not desirable because most of the graphs that you are given in applications are not bipartite. Therefore, if you want to use this theory, you need to do bipartite graph learning or some type of approximation. And on the other hand, the normalized Laplacian is also not a very popular, or it's not as useful also as a variation operator, and most applications tend to use the combinatorial graph Laplacian. So therefore, based on this, we sought to find like a more general theory, and what we obtained is that we can actually remove the bipartite assumption and the normalized Laplacian assumption, and we can actually have two-channel filter banks on arbitrary graphs with arbitrary sampling sets and also with arbitrary positive semi-definite variation operators. And all this while still having the desirable properties such as perfect reconstruction, energy preservation, and critical sampling. How do we do this? Well, we basically use MQGFT and we construct it in such a way that it satisfies the spectral folding property. And then we use this to basically extend the results from Naranja and Ortega to prove that these filter banks can have these properties that we like. So this is how we proceed. So let's assume we have a vertex partition, arbitrary. We have a variation operator, also positive semi-definite arbitrary, as shown here. Then our main result is the following. So if we choose the matrix Q as follows, which is basically the block diagonal component of M, and if this Q is positive definite, then the MQGFT exists and has the spectral folding property, which means the eigenvalues and eigenvectors of the fundamental matrix have the spectral folding property. Now, to apply this to construct filter banks is as follows. Let's say we're given a variation operator M. We can pick any pair, any vertex partition AB, and then given this vertex partition, we have a way of picking the inner product matrix so that the spectral folding is satisfied. And then we use spectral filters based on the fundamental matrix C. And then we have the following results. So we have perfect reconstruction if and only if these two conditions are met. And we also have energy preservation now in the Q norm if these next two conditions are met. Well, this is great because these are the same conditions that are well known for bipartite filter banks. Therefore, now we can reuse any of the previous known results from the past 10 years about bipartite filter banks, as long as, and they are generalized to arbitrary graphs, as long as we basically implement the filters using the fundamental matrix. And now I will show you some experiments comparing bipartite graphs against non-bipartite k-nearest neighbor graphs, and in a point cloud representation application. So point clouds are a list of points in 3D. Each point has a color associated to it. And since point clouds are 3D representations of objects, they have applications in sort of virtual reality and immersive communications. So for downsampling, we will just use random selection of points with probability 1/2. As variation operator, we consider the combinatorial Laplacian, and then we compare two types of graphs. One is just k-nearest neighbors based on the point cloud geometry, and the other one is basically taking the k-nearest neighbor graph and only keeping the edges going from A to B. As a filter bank, we use a very simple filter bank as shown here in the figure, which is basically polynomial on C of degree 1. This is our first result. So here we iterate this filter bank for 7 levels and keep the m largest coefficients and set the 0 to rest. And we implement it in this long dress sequence, which has about 800,000 points. And then we observe that basically the best result of our proposed method in the blue line is obtained with the sparsest graph, basically with k = 5, while we always outperform the bipartite implementation, and this bipartite implementation also doesn't perform as well with very sparse graph. It requires a little bit a more dense graph. You can see the differences in terms of visual reconstruction. Very sparse graphs with that are bipartite really have a lot of artifacts. And here's another example on the texture of the dress. In terms of complexity, the main difference between our methods is that in our method we need to solve a Laplacian system of equations, while in the bipartite case we need to do a bipartite approximation. We run some experiments and we observe that our method is about 20% faster. In conclusion, we showed that the spectral unfolding property can be generalized to arbitrary graphs and arbitrary variation operators, and the bipartite assumption is not required. We can also reuse many of the filters that were derived for bipartite graphs. And in terms of practicality, our implementation can be even better in terms of computational efficiency and also in terms of quality of signal representation. Future work, there are several open questions. One of them is basically how to choose the inner product matrix and the vertex partition. So since our method worked for any vertex partition, there should be ones that are better than others. So some criteria might depend on the application and also on computational considerations. Another alternative is how to choose the variation operator. We have a paper in another session that looks at this problem. And also how to interpret this inner product cube. Thank you. So if you want to know more, you can see Dion's presentation, and also we have a longer paper with proofs and more details online. Thank you.